Thank you for attending AltiumLive 2019. We appreciate your attendance. And my name is John Magyar. I'm an FAE with Altium, have been with the company for over a decade, and I've enjoyed working with the product and see the product evolve into new products and things. And it's always been a very exciting place to work. And another aspect that I enjoy is actually visiting sites where I get to see what you folks do day in and day out. Sometimes I'm kind of jealous with that, but I learn a lot about what you do, and my goal is to help you folks be more productive with the technology that we offer. So it's a very good exchange of information. I see what you guys face, and then I try to provide solutions to help make things more productive in your space. So this morning, we'll be taking a look at how to analyze power in your PCB designs. So this can be a critical factor. Has anybody had a design that exhibited problems that were power related? Okay, so good to have some references there. And so we'll be talking about some of the common types of issues that occur and what their impact will be. And primarily, I'll show you some methods of trying to discover these issues earlier in the process. So that's the focus, that if you uncover issues early, before things get out into the field or mass produced, then it's far less expensive to resolve. So what is a PDN? You hear the acronym. The most common definition is Power Delivery Network. I've also heard Power Distribution Network. Either way, it's an acronym for the collection of components, traces, planes, and interconnect that form our power supply and actual connection to the load devices. So it's that critical network, and here we have an example where one of the nets is highlighted, showing the traces throughout the board from the source over on the right, and how that distributes all the way over to the far left. Pretty simple example, but the principles that I'll be talking about are the same, that we want to ensure that in your power delivery network you have adequate supply of voltage to each and every load device. So that's the primary goal of using this. So why has this become such a concern lately? Traditionally, electronics was pretty bulky stuff in big metal boxes, backplanes and boards with lots of space to work in. And when that's the situation, you can build in a lot of copper to conduct the power distribution, and it's never really a concern. So you have lots of space, you can throw lots of conductive copper at the problem, and then there aren't any issues. But with today, if you take a look at a cross-section of consumer products, so things such as lightweight, wearable devices, and even that image is probably outdated now. We're making things smaller and smaller, flexible circuits that are actually built into clothing. The problem there can be that high density leaves very little room for conductive copper. So the copper you do use, you want to make sure it's adequate. In the center, we have an example, typical example of something that's high speed. And all of the high speed components, naturally, power requirements are critical to make sure everything has adequate voltage at the load components. Otherwise, we get failures, system failures that can be difficult to diagnose. And over on the far right, if you look at the typical gaming PC, very power-hungry applications, consuming lots of power. So that's another type of design that you would want to analyze to make sure that your traces and conductivity can appropriately handle the current flow. So power is not just a concern for high-power products. It's also with smaller devices as well. So what are the common symptoms of a power-related issue? Here we did a survey a while back where we talked to a cross-section of our customers doing different types of designs. And we got some interesting responses. So things like CPUs resetting unexpectedly, or FPGAs that don't configure on power up. In the analog side of things, circuits that would drift in and out of design specs. And I won't read all these, but you can see there's quite a variation of different types of problems. And some of those problems can be heat related as well. So if you're moving a lot of current through a small conductor, that can tend to heat up. Boards warping, laminating, delaminating due to heat issues. And a couple people raised their hands. What types of issues did you encounter, if you're at liberty to say?
I have a big array of solid-state switches that if you tried to switch a lot of them at once,
Right.
they would create a big enough ground bounce to kill the power supply.
Okay.
The analog power that was controlling feeding those switches.
Exceeded the current capability or current supply.
And actually over-voltaged it
Yeah.
in a way that it didn't like to happen.
Okay. So it's a perfect example of a worst case scenario. As you're designing, you may think, well, these traces are adequate, but what about that one corner case where everything is on instantaneously, and it may be tough to see that, and the routing may appear to be fine, but that's a typical example of what we commonly hear. So, I've worked with customers who have found problems in the field in the past, and then they asked us, could we look at those designs and see if we could spot them? And in most cases, we're able to find things such as severe voltage drops that were noticed. So a device that's not getting enough voltage to properly operate, the board will power up and start to run, but then at some point you hit an issue and it can be difficult to diagnose. So that's generally how power problems are discovered. It's not right away in the lab, but after some usage and you hit a corner case, and then you know there's an issue. So if you want to maintain optimal cost and reliability, it's best to find these types of problems early. So this is a common thing that I hear. My boards work fine. Why should I use power analysis? And as I just said, it's board may perform well under most conditions day to day, but then when you hit that corner case. Another thing, marginal power routing can lead to thermal issues as well. So poorly routed boards can have a tendency to increase in temperature. So you have higher resistivity in the traces. You're going to draw more current, and that can result in heat problems. Component tolerance and process variation as well can lead to power issues. So things may work with one batch of components, but 2 years later, when you have the board manufactured by someone else, they put slightly different spec'd parts in, or maybe just another supplier or manufacturer of a part, and that can reveal a marginal issue. This is one of my favorite quotes. I'm not sure if the gentleman's here this week. Tim Tabor. He does a lot in the aerospace industry where things they're sending up in the air pretty critical. So his analogy or statement is we don't always see the forest through the trees as engineers. We're racing through something and a certain approach looks good, traces look wide enough, but then when you really analyze something, you can see areas where you do get voltage drops, or you may get areas of high density, and that's what he's referring to here, where the current density through some vias was measured at 48 milliamps per mil square. And just by moving things around, or sometimes you can change the diameters of the through-hole pads or vias, and you can reduce that current density. So reduced current density, you avoid thermal problems and things like that. So I'll talk a little bit more about some of the issues. But that's a very common statement that our boards work well, we haven't had any issues, but problems do happen and things get overlooked. So DC power is pretty straightforward. It's simply a matter of voltage, current, and resistance, simple Ohm's law. And when we have a supply and a return rail, if not routed correctly, even the slightest amount of resistance, not even a full ohm, so let's say a quarter ohm of resistance, in this case in both supply and return path, can lead to the loss of half a volt at the load. So pretty basic scenario, but just that little bit of a variance is enough to create a marginal problem that takes a while to reveal itself in your product. And hopefully when it does, it's not at high volume production. So just something to keep in mind. And another thing is that the actual resistivity of copper, it's an excellent conductor, but depending on your application, the resistivity can change based on temperature. So if you're working at room temperature with an average consumer product, that's fine. But something that can be in a harsh environment, say an industrial setting, or a lot of times mining, underground equipment, boring equipment, will incur temperatures that are very, very high. And the property of the copper is such that it will become more resistive as temperature increases. So here we see a little graph. We have pure copper on the right. And another thing to keep in mind is that the copper that you end up with on a PCB is, I wouldn't use the word impure, but it's not like the pure copper that you would find in wiring. So because of the process of how PCBs are fabricated, the copper goes through a little bit of chemical etching and whatnot, so that deteriorates a little bit of its conductive property to begin with. And then, of course, the effects of temperature need to be taken into account. So one of the typical problems that we hear about are voltage drops that cause some type of failure. So how do these start in the first place? Well, if you've ever routed boards under deadlines, which I'm sure you do, there's a lot of pressure to complete a design. And things may start out fine in the beginning, but towards the end, you find squeezing those last few traces in to complete the routing can sometimes compromise ground and power. So here's an example that's circled where there was a nice wide copper pour for ground polygon, but just squeezing those last few vias in to get everything completely routed started to chew away at that path. And that's one spot where you can get high current density. Probably not super critical, but situations like that are introduced because we're trying to complete one thing and then not seeing the full picture, we inevitably create another issue. We complete the routing, but we compromised the power delivery. Over here on the left, we see an example where, and I've seen this, where split planes can start to get hacked up a little bit, or they may meander around the board. I've seen this a lot with polygon pours. Components get moved around to solve some other issue, so placement is addressing one type of problem, probably to complete the routing. And then yet that creates now a problem. How are we going to get the power in the plane layers out there? So I've seen sometimes a copper path in a plane layer that actually made an S through the entire board, and that was one that did reveal a true problem. So we're under pressure to solve issues, but can miss newly introduced problems. So let's next talk about the relationship between area, current density, and heat. So, looking at voltage, that's one thing, making sure we have adequate voltage level at the loads. But copper paths can sometimes, as I have shown, be compromised. And the way current density is considered for power considerations is it's a cross-sectional area of the copper conductor. So it's typically the width times the height of the trace that makes a cross-sectional area, and that's how we calculate current density. So how much current is flowing through that square area is the measure of current density. We also need to consider the length. So if you have a really long trace, if it's a very narrow and has very high current density, then you can get loss over the total length of that line. So that's another dimension of things to take into account. So it's voltage, current, and voltage drop, and current density increase. So these are the things that we're typically looking for to make sure we have a high quality power delivery. So high current density, due to an inadequate amount of copper to conduct the current, can lead to issues like this. So these are just some pretty random, typical examples. You can have fuses or traces that will actually fuse open because the heat can be so much the copper will melt. I have seen this happen on very tiny traces where there's a fan out and the very thin parts of polygons can sometimes fuse open because the polygon is poured. Again, when you originally designed the polygon, it may be perfectly fine, but after components are moved around, vias are introduced, you can come up with some areas where you get little bottlenecks in the polygon and those can fuse open. I've had many customers report that over the years, and since introducing this capability that we have, I'll show you today, it's really the way to find that. That's not something a design rule can always pick up. So, high current density is a concern. You always want to know how much current flow is at any given point, or simply knowing, hey, what's the highest current density in my design? And then, you can typically move things around or make some modifications and lower that considerably. So I'll show you some examples of how to do that. And then if we look at the other end of the spectrum, so what about too much copper? So particularly with smaller devices where we're space constrained and we're trying to route as much as possible in that small area, we want to know what can we reduce and how little can we get away with and still have adequate power and ground traces. So that's kind of another aspect of using power analysis. You want to make sure everything's adequate, but you don't want to be carrying extra copper if it can be avoided. So, with things becoming more miniaturized, power analysis is helping out in that area. So what are the ways to verify power delivery? Traditionally, a lot of designers wait for the first prototype, and I hear this often that, well, that's the true power on the bench when we fire it up, and that'll give us the actual measure that's better than simulation. So that's true. A couple things there. You may not hit the corner case in prototype, and simulation can take into account worst case scenarios. So you can vary your analysis by creating different tests, and therefore you can come up with high temperature tests, or you can come up with different corner cases, different temperature, different worst case loads and whatnot. So you can play around with the variables and then be sure that what you have will likely do well when fabricated. So, generally it's probably a combination of both. Thoroughly analyzing the prototype, but also making sure right out of the gate, just doing a little bit of math and verifying what you have can go a long way and save you some problems. So just a graph on the relationship of when you discover the issue. So if you discover it in layout, the cost to resolve that is obviously the lowest. If you get to the first prototype, or maybe second prototype, that's not in the field yet, but that's considerably a bit more expensive. And then once something goes into full-scale production, to spin a production rev will be the most costly. So that's what you want to try to avoid. So again, doing some common sense analysis up front can reveal some issues. So another concern is how do we integrate something like this into our design methodology? So a lot of people start thinking, well, I have to add another tool into the tool chain and maybe get a specialist who looks after power considerations. But there are ways to integrate that directly into the PCB editor itself. And that's what we can look at. And this will help you get an early insight as you're designing the board. So, right from the beginning, you can get some early results based on, partially routed board, or just to see how things are starting out. And you can always run this iteratively throughout the design process. And this will help you explore layout alternatives as well. So, getting that information up front will give you some alternative routing approaches just by taking that into account much earlier. And again, the important thing, PDN analysis lets you set corner case conditions to be assured. So as the example this gentleman gave, if you had described that situation and loaded everything down in a model and then saw the current, that might be an indicator that, that much loading would have an issue. So particularly things with timing, there's things that happen infrequently where all loads are active at once in their worst case condition. But that's something that's easily simulated. And the big thing is reduction in cost. We try to find problems early, but another thing is if we can determine some alternatives to the routing, it's possible you may be able to drop a layer or two, not always, in the board fabrication, which you can save on there as well. So reduction in cost, a smarter design approach by handling power up front. So best practices to avoid power-related problems. First thing would be to adopt what we refer to as a static solver-based PDN analysis. So don't wait for the first prototype. Verify early and resolve marginal voltage levels at critical devices. So we can take a look at that. I'll walk through an example. Carefully inspect anything that shows high current density. So if you're drawing lots of current through one particular area of the board, that can be a problem for the conductors and the physical laminate of the board as well. And again, ensure that you can handle worst case loading conditions. So it's, again, easier and less costly to visualize these types of problems up front rather than later, once something's in production. So next we can take a look. I'll step through and show you, it's a pretty straightforward system, but it lends itself well to the typical scenario where we have multiple DC supplies. And I'll show you how to define your power sources and loads. And then we can run an analysis and see what we find. We can view the results interactively. So it's a very visual tool. And then also there's a lot of reporting capabilities as well. Then we can do an update. So if we find any problems, we can make a change that in the layout, and then rerun the analysis and see if we've corrected an issue. I'm doing this on Designer 19.0.15. I just want to mention that in case any of you want to try this out and do an evaluation. The later versions work. However, there's one tiny little anomaly, which I think is pretty important. It's actually in the reporting that's yet to be fixed. So that was introduced after this specific version. So, if you're interested in having a look at this, just jot that down. That at this point in time is the best release to use. There is a reported bug which is being addressed. I'll point that out. It's actually somewhat minor, but I think it takes away from the ability to see successively where your hotspots are. So you want to see first the hottest spot on the board. The newer versions can do that, but what's nice, this feature would let you click and see, well, what's the next hottest spot, least, and then sort of descending order of hotspots in the board. So I'll show you that capability in detail. And we'll take a look. So actually, I'll escape out of here. And then typical board in Altium Designer. As I said, this is a fairly straightforward design. It's actually a real piece of hardware that Altium provided years ago. It was just a small embedded system development board. And it has 3 voltage supplies in it. I'll bring up the power schematic page. And fairly typical supply voltage coming in. That's 5 volts DC, and very simply a 3.3 volt generation through a linear voltage regulator, and likewise a 1.8 level voltage for inside of an FPGA. So that's the internal core working voltage, and then the 3.3 is the I/O of most of the devices, and then there's a typical 5 volt level for some older components. So pretty much what you would see in designs, but you can get designs with dozens of DC voltage levels, and that is fairly common. Another thing to keep in mind is that the circuitry to do that isn't always these nice voltage regulators. You can get complex power electronics providing your source. So things like power transistors, and all of this is fairly straightforward to describe. So I'll show you an approach that's very general, and we start to think about our design in terms of, okay, what is my power source furthest back? Which things cascade through other components? So it's very common for you can see a hierarchy of voltage regulation. And I'll show you how to deal with that. And then other times, as I mentioned, power regulation can be almost analog art, where you don't always have these nice packaged regulators. You want to come up with some very creative circuitry. The tool can certainly be used for that as well. So we'll focus on this area right here. So power comes in, goes through a fuse, through a switch, and then out to the regulator. So here's the main 5 volts, and the regulators will produce the lower level voltages here. So these are simple linear regulators. So to get started, you can invoke the tool. So this will be the PDN analyzer. This is a capability that will be added to Altium Designer as an extension. So if I go over to the extensions page, in the top right corner, if you ever look at your extensions and updates, you can click on the purchased area, and actually mine's already installed, so you won't see the tile there. But if we look in the installed, you'll see there's a PDN analyzer tile. So to get started, you would make sure this is installed here. It does carry with it, it does require a license, but that's generally an add-on type of thing that's pretty straightforward. So the first thing we want to do is define our power nets. And in this case, I can reverse back through this process. So if I actually sort of select these all and then remove them. When you first open up a design, your power signals are sometimes pretty obvious, and the tool will try to infer which ones they are. It doesn't always do a perfect job, but it's a big help. And generally, you get things lined up that end in V, or naturally GND or PWR. So these are all very common things that, when you first jump into a board and open this up, it'll detect these signals. You might have to go and add additional signals. So I could do that right now. So here's one that's typical that I know I'll need. It's a particular net. So it's a net that's not named by a net label. So usually, if you give a nice name to something, the tool can find it. And this way I'll select this and add, select it. And I can uncheck this and kind of go back and pick up the other ones as well. So I can add the ones it found with the levels. These levels are all correct. And I can just say add over here. So now that I have that listing of nets, that's a process that takes just a few minutes to go through your entire design. You may have 20 or 30 pages of schematic. It can go through and find everything. And then you may have to add a couple here and there just to guide it. But with these, it now knows that these are significant in terms of the naming and their value. So this comes in handy with the tool creating the description of the power network. So I click OK, and that's saved away as what we refer to as DC nets. So you can go back and add these or modify this list at any point in time. So the next thing we want to do is to create a new power description. So we can say new simulation, and we'll start out with something that's unnamed, and then we will start to build that up. So to get started, I'll click here on the network, and the first thing it wants is a power rail and a return rail. So generally I just click in there, and I can get the name. I'll start with my power in. So that's the connector, and that's going to be truly my source for the whole design. Naturally, I would want to find the ground return signal. So now I have simply power and ground. Once I have a power and ground, it will allow me to add a source. So I can add a source component, and it's ready to connect that to these nets. So it's already filtered out a lot of things that don't belong connected. And so when you use your pull down here, simply J1, which was the power connector, automatically populates. And over here, I can specify what the voltage level is. It's picked that up from the DC nets that it inferred the name, or if I filled that in manually, it would get that. And at this point, you can still change this value. So if it comes up without a value, you can always tweak that and add that manually in this column. One thing the tool doesn't know is what the output current would be from that source. So I might say something like this has a 4 amp capability, and I could further specify max power per pin, or I could leave that at 0. That's an optional setting. And now when I go ahead and click OK, I have a power source that's 5 volts, and it knows its max current capability is 3 amps. So that can be used for checking. So if I've exceeded the current draw, I can then flag that as a violation. So I can do these types of cursory checks, things that you really can't do in the regular DRC. So now let's take a look at drawing this out a little more accurately. And in future releases, we're considering things like maybe embedding some types of compiler directives to make this easier. So you just drop these things in the schematic, and it will create all this network for you. So from power in, I want to go through this fuse and through the switch, and we'll very quickly build up this, this path. So one of the things I can do is extend this net, and I want to extend power in to the next level, net D1, and that will be my, that's the fuse, that's F1, and that I'm not concerned about any parameters there. And then I can add a second series component. So this is what makes it very easy to describe the topology of the power system, because generally a lot of things flow in and out of multiple devices, and those different nets can be complicated to follow the path. So this is what makes it easy to go through, and we just keep extending the net. And now when I want to get to 5 volts, I'll go and select that. And now I have my pretty much my main power net described. I would give this a number. So this is the switch, and it automatically connects the pins. So it's building up that connectivity that's needed for doing the analysis. So at this level, I can add a load. Now this board has many components. I'm not going to do all of them. I'm going to show you an example of how we can create all three voltage levels as a hierarchy and then show how they're related. So first, I'll make add a load here. And what I want to include is one of the voltage regulators that we saw. So first thing I can do is choose from a category of components. It could be a load IC, or could be a resistive load, or voltage regulator that's linear, or a switch mode power supply regulator. So you have these choices. And then one more variation is switch mode with a sense line. So we're going to go with linear. That's what's in our design. You see a little image here. And it's actually going to look at this model and consider the input, output, and what's happening in a typical regulator. So now I'm going to specify the actual load instance. So this is U4. I'll show you this in the schematic when we go back. And U4 is supplying the 1.8 voltage, which is the internal core voltage, or VCC internal. And then we have ground. So these are the three signals we have to connect. And so here we'll go back to U4. And you notice there's no direct connection to ground here. That's because the ground connection goes through a resistor. And we'll just simply add that as that's R19. I'll show you this in the schematic so we can see what's happening. And that's going to have a different output. So once that's connected, so input is 5 volts, output is going to be 1.8. And our current capability on this one, I believe that's roughly 2 amps. And max power dissipation, won't do anything there. I'll just go ahead and select this. So now I have a load. The neat thing about this is that you can always get back at those specs at any time. Just hover over it, and you can double check and see what's listed there. But the real neat thing is now I can add this to a new network. So this green block here is now the source at a lower level. So just to show you what we did, we've described everything up here. We've added U4, and now U4 will branch out, forming its own network. What's nice about that is the tool has a sense of continuity between this regulator, this net, and traveling back through to the supply. It's not carved up or separated out by nets. It's a truly continuous hierarchy. So if I hold the control key, double click, I go back up to the top. Hold control, double click, descending down. So you can literally move through your complex power distribution that way, making sure everything is adequately structured and you have an accurate model of it. So primarily we want to worry about the voltage level and the max current capability the part can deliver. So again, thinking worst case, what's the absolute maximum this part can supply before there's a problem. So you can get that information from data sheets. And now I would start to add the loads. One interesting thing I'll show you is how some devices can have multiple supply levels. So a typical IC will have maybe 3 DC voltage levels provided and connected. So we can handle that scenario. I'm going to add a load here. And this load will be just a regular type IC current. and I'm going to choose U1, which is our main FPGA. And to show you something interesting is I can look at every connection and choose whether I want to include that in the analysis. So all the power connections now for ground, what happens sometimes is things connected to ground aren't really in the power circuit. They may be logically tied to ground. So I have the option to uncheck things that are logical connections to ground or power, and then include that. So that's a nice, accurate way of defining what the load is. We'll say a load current, maybe this might be 500 milliamps. And the voltage level, I can just say, let's take a plus minus value of that at plus minus 5%. And then we can finish that. This design does have many loads. I'm not going to go through them all. I have another predefined configuration we could look at. But just to take you through the process to see how this is described, we'll walk through and add another load. So I'll go back up to the top, kind of walk that hierarchy, and now I can add a second voltage regulator. So this time it's going to be my U3, which is the 3.3 regulator. I have to tell it that it's a voltage regulator, and the output is going to be VCCO, and then I just simply provide the reference designator. Similar situation, ground is connected through a resistor, which is R14 in this case, and I just have to connect that by selecting it. And then go through the same thing here, set the voltage level, 3.3 volts, and a max load current of, let's say, 2 amps. And now I have a second one. So this can be added to U1 as well. So I'll have to do that same thing where I right-click and then add this to a new network. It forms that. And then I can just right here add the FPGA, this time, U1, and it comes back with all the connections. So likewise for ground, we want to take out those logical connections there. And a load current, maybe this is 200 milliamps for this branch, and then that's plus minus 5%. So now I've created a second load. And if we want to take a look at the entire network, I go back up to the top, and we can see how this branches out, and then there's an ultimate top level of how it ties all of that together. So what's nice is when it's calculating current draw, it has this picture of it. It's not sections by voltage. It does have some smarts to know how current flows through different types of voltage regulators. So there is a little bit of a more advanced model for regulators in particular. But for the most part, the functionality of components isn't considered. So this isn't like SPICE simulation. We're not simulating versus time or relative to time. It's simply a static calculation of your supply voltage, your resistive load, and the flow of current to and from. So it's very basic, but can tell you a lot about the design. So that would be a typical setup. And for a more complex design, it's the same approach. Can generally be done fairly quickly, and once you've done a couple, it goes through pretty fast. What I'll do is show you some other capabilities. I'm going to go ahead and save this, and maybe save it as a demo version. And it already exists. I can overwrite that. And what's nice is that I can clear these out and reload others. So that's what I'm going to do at this point. I'm not going to run the simulation on this. That was just to show you how things interconnect. So I can remove this description, and then I can bring in some other ones that I've very carefully constructed over time. And you'll notice that it'll say all power, so it's considering all components as loads. And there's a nominal identification. So that would be worst case under nominal temperature conditions. So we can take into account the ambient temperature. And in these two scenarios, I have a higher temperature rating that it will stress or recalculate that copper conductivity, and I'll show you that in a minute. So I have three corner cases here, a baseline nominal, and then two others for temperature variation. But you could create any number of corner cases depending on whatever you're interested in. So it doesn't have to be temperature. You can make these worst case situations. Another thing I mentioned that it's a typical simulator. You think you're simulating relative to a time clock. As I said, this is static. So I've seen some pretty creative things where it's a brushless DC motor controller, for example. That's something that one half of the circuit is working for X period of time, and then the other half works for a similar amount of time, but they're never on at the same time. So the scenario you would do is you could make a configuration where one side is activated and then the other, or actually it's three in the case of a motor. There's three phases to that. And you could build up a scenario which measures each one independently. So to get around that absence of time, you can make more configurations to describe a particular condition. But I'll load this up, and configurations are a nice helpful way of managing that. And as you can see, I'm just gonna clear the results. This was run previously. I'm going to delete the simulation results, so now it's starting by removing all of what was recorded earlier. And to actually run this, before I do that, we'll look at some other things. There's a settings that goes along with this topology now. And in the settings, I was talking about the conductivity of the copper earlier. You can vary that if you wish. If you stick with the default of standard PCB copper, this is based on what's typical for your average PCB fabrication. But if you want to tweak the values, you can. There's a via wall thickness for plating. You can look at this in either metric or imperial to get your plating dialed in. Here's where you can change the temperature. So if I make this 40 degrees instead of 25, the resulting conductivity and resistivity numbers change. We'll put that back on 25. And here's how you could make yet other temperature-related configurations and corner cases. So there's a lot of flexibility in the types of things you can run. It's not like you're just pushing a button and it runs it and tells you a bunch of things. It's you can craft the type of test that you want to perform. So that's mostly here, conductivity, via wall thickness. We can also set limits, limits for current density. So these would be non-via, in this case up here. So any surface layer conductor, I could give an absolute maximum current density. And if it's calculated that that's exceeded, we'll get a violation. And again, that's not something you could do in the DRC. Internal layers can have a max current density. For vias, this is very handy to understand how much current is flowing through a via. Vias can fuse open if they're tiny and the plating's not thick enough and there's too much current flowing through them. So what we have is a way to describe the smallest hole size and the largest, and then we can set a constraint on what that lowest level current capability would be, and then the highest. And then that forms a reference for every hole size that falls in between those two endpoints. So we get checking there, and that's what I have set up for this one. In this design, we're going to look at how much current is flowing through the vias, and do we exceed anything? So I've put a known error into the design so we can find it. But that's how we can set limits and constraints for the power analysis. Just one more thing here, just some minor stuff about how you define current density. That's typically amps per millimeter square, or you could do mil square or meters square. You'll see a lot of reference documentation, but generally it's amps per millimeter square. And enable, these are just some stray options here. Current density noise filtering, so it kind of reduces some of the repetitive rounding and things like that in the result. So these are the two main ones, limits and simulation. I'll actually just cancel that. Anything else to look at from here? There's a nice way to toggle back and forth. We'll see when we get results, we can look at and explore, and this is very powerful. We can literally walk each trace and see what the voltage is, what the current density is, and find hotspots in the entire design very quickly. In the configuration panel, at this point I'm ready to run the simulation. I always do a double check here. You'll see these green and blue checks. That basically indicates that the tool is satisfied that everything's been fully configured, and actually it does that in an order. It's order dependent. You can't get to the run button without satisfying these in a specific order. So it's doing some double checks to make sure you have an accurate setup. I'll go ahead and hit the analyze button. What this will do is look at all of the copper and extract that out, and does that using its ODB++ format, all transparent to the user, so you don't have to worry about generating that output. It's doing that in the background, so it gets that accurate physical description of every layer. So all of your planes, polygons, and routing. It'll reconstruct that copper and then pass that to a static engine. In this case, it's produced by a third party called CST. That's all they do, are simulation tools and analysis tools, and we simply access their technology and put the interface around this so that you can harness that capability. So now that this is complete, it puts me into the visual tab, and I have some results to look at. So let me close the schematic. Whoops. We'll go back to the board. And if we look here, we can get a 3D image of the board. So we could start to look at voltage and current density. So you can see it's, let me just move this out of the way. It's created this band here, which is defining the color gradient. So the highest here, or redded, that's 100% of the highest current density value. And then the lowest level would be 0 or no current. So right now we're looking at current density in this design. So anything red is going to be the highest current, and that's accurate, showing what's coming in on the connector to the board, and then as it goes through the regulators, it starts to become less dense. So let's look at voltage. We can see, again, the highest voltages over on the right, and then the relative voltage drop. This doesn't go all the way down to 0, but typically there'll be a low range. So you'll see your range of voltages represented here. So the neat thing that I like is, if I want to, right away, I want to know in the entire design, not the view, but if I select this design, tell me my minimum voltage. So I check this highlight peak values, and I want to look for the minimum voltage. Voltage is selected, and when I hit locate, it'll jump to that point. So as a designer, that's really what I want to get to, is what's that lowest value. And I can then probe this, pick the location, and it lets me pick that with a mouse click. So I hover over this spot. You can see that spot is highlighted anyway. And I then add this to a report. And it captures that image. This is really nice because if you ever spot something from an analysis tool, you have to go talk to somebody about it in a design review or whatever. So this is a nice way of capturing the conditions that you want to discuss. So that's the absolute lowest voltage level on this board. By contrast, I could go ahead and save that. I'll just give this a name. So lowest voltage, save that, hit done. Then I could move, I'll move out of that. Then I can jump to the highest voltage. So we could select maximum and then locate, and that'll bring me over here. And then likewise, I can simply record that. It's going to record the extremes anyway, but if you wanted to, you can use this capture to get everything and say add to report. So now I have two images that are physically added to a report that I can refer back to, for reviewing a static document. So you don't always have to bring up this viewer and show everybody. You can capture this in a nice HTML report. So we'll save that. That's going to be the highest voltage. We'll save it and then move on from there. The thing that I go for very quickly is current density and where is the maximum, and I want to locate that. So that's going to take me right to this. Actually, this simulation, when it completed, it threw me into this view here, which is convenient, but it does some checking at the high level. So if I go back to the configuration, you'll see some red marks are highlighted. So when I was showing you that you could place constraint checks on the vias, so it looks like that's what this is. If I click into this box, and you can hover over a message at some point or click it, it should, yeah, it'll give me a little message indicating that a via was found where current measured was 900 milliamps and the limit was 850. So we exceeded that slightly. That's why we put checks in our design. And very, very visual indications are that have found that. So what I would typically do in sequence, now go back to the visual and say maximum current density, where is that? And then I can do the locate. And in this case, it's actually taking me to that via in question. So this has, let's see, we're in 3D. I can kind of navigate around here and you can look at this. So one thing I notice is, wow, this looks pretty narrow in general. And then easily enough, I can flip back to the 2D, and that via is right around here. Okay, right there. So it still has the highlighting of the analysis over it, but I could click on this via, and then I can view that in the properties over here. So this will show me the via size, and I can switch this on the fly, so I might want to bump that up. It's so it looks like a whole size of 50. May want to make that much larger. The whole size 60 and an outer diameter of 90. That's more typical for the via that I would use there. So I can switch that on the fly, and now I'm going to save this. So I've updated my design. I've actually, I could clear this out just to show if I go back. So after doing an analysis, let me go and just clear the results. And now you can see I replaced the via. So let's rerun this again. So the first time it went through, I had a violation on the VCC internal net, and it was due to this via being too small, and it printed out that violation. Let me go through. Actually, one thing I want to show you, if I go back to visual, I cleared the results. I'll show you on the return trip there. We can rerun this, so you can always get back. You can actually save this and then come back at any point in time. Just simply invoke the PDN analyzer, go back to config, and now we're going to rerun the analysis. So the design physically changed. It'll go through and extract that copper information again. And is that running? This should run, and now it's complete, and then there's no error this time. So let me rerun that fully just to make sure here. Don't think that. I'm actually going to clear the results and reload that all. Actually, if I just remove this. I'm going to reload the nominal. And we'll take a quick rerun. And this time there won't be any violations with that change in the via size and rerunning the analysis. After this, I'll generate a report, and we can look at some of the finer detail that's available to you. If you've ever had to look at one of these scenarios and debug things, it's nice because you'll get actual values for each pin and each via in terms of voltage and current. So this puts me back in the visual. I can see all green checks now. This branch is passing because we changed that via size. So that's the kind of iterative approach I talked about. This is highly integrated into your design tool, so you're not going out to an external type of analysis tool. It's all very convenient and allows you to analyze as you're designing or at that final stage of finishing a design. So next, I'll focus on that reporting capability, and we'll take a look at that, what it produces. I'll just generate some things. So we saw before we could do image captures, so I'll just take a couple images here, and whoops, gotta select that, select the point, add to report. I'll just want to create a couple images to have in the actual reporting. Okay, and I'll save that. Just so you can see how valuable this might be for looking at design issues. So you can choose another location, select this, and then add to report. It'll even allow differences, so I can save that and say done. So if I pick location 1, let's say right on this net, and then select difference, location 2, it'll report back the difference of those 2 points. And I can say add that to the report. So now I have 3 images that are saved and can be used in a final report. Go ahead and there. And then here on the lower right, if I click Generate Report, it allows me to check or uncheck these various capabilities. So if I want to include artwork or the system captures and things like that, the images, I can check and uncheck what I want to. I'll leave everything checked to show you what it does, and then simply generate the report. In a couple seconds, you'll have an HTML file, which is viewable in any web browser. Here it gives you the location of the design and design stack up. So this shows the physical properties of what was used to calculate the results. So it actually is looking in the layer stack up, and your copper thickness, the dielectric of the core, it takes all of this into account and records this information for you. Artwork by layer just gives you an image of each layer. Again, very helpful to have this in a design review when discussing a particular issue. And again, the parametric settings for the analysis itself, the temperature, the conductivity, all that, via sizes, and shows you the network topology. If there were violations, they would be reported here, highlighted in red. And then you get your image with the snapshot of the probe. So if you had those areas, you can actually zoom in and focus on that and take those snapshots. It doesn't have to be a probe point. It can be a very zoomed in image of something. But the idea that you can pull images in is extremely helpful in a report context. And then gives you the network details. So here, we actually get down to the actual pin. It'll show pin information for a part and what the values are. That's actually probably in a different form, but I'll show you that. But you get the idea. It gives the details for the full design. And this is just the other branches here. So VCC internal, the report on that. So I'll close this and we'll go back to this information here. I just want to show you this one last thing. So within here, we see there are pins. So for every component instance, I can scroll through and get the actual net name and the voltage level. These are sortable. So if I click on the heading, I can very easily see the net or pin of highest voltage. So particularly helpful for pins and vias. So from a physical standpoint, if I check my vias, what's the via with the highest current calculation? And there it is right there at 1.799 amps. And I can very easily get to that location. Actually, I think a double click will get me there. If I double click as I move around this list, you can see it jumping in the background to that location. So, again, if you want to investigate, questionable current values in vias, you can sort this list. Same thing for voltage. At the top of the via, at the bottom of the via, it'll give you a voltage 1 and 2. That's the voltage through the via. You can sort highest to lowest and then jump to the particular object in question. So all in all, it's meant to be a very easy to use, basic type of utility. A common question is, well, what about thermal in terms of analyzing the temperature of the board from the heat generated by the parts? So we don't go into that level of analysis. That's actually far more complicated. This is meant to be a very basic tool. So pure thermal flow is more complicated. We'd need a different engine to do that. And another thing is, we're not in all cases taking into account the enclosure. So you get airflow and things like that. So we're really not set up for that type of analysis. That's something you could do probably in any number of analysis tools, such as SolidWorks. I think they have a thermal analysis capability, and that would take into account the full enclosure and other environmental factors. So what we're looking at is a way to make sure that all conductivity from a source to each pin of the load is adequate, and you can set checks similar to design rule checks to flag things that would be of great concern. So maximum current through a via, lowest possible voltage. You want these things to jump out so that you can flag them and then find a very efficient way to navigate to those particular issues in the design. So I can take the mic around if anyone has any questions. Just ask that you use the mic for, so we're recording this live. So if anyone has any questions. Yep. Go over here. So.
Is it practical to simulate dynamic analysis by setting peak expected currents that may be very brief? Mm-hmm. I recognize this is a DC analysis, not
right.
an AC, but is that going to give you helpful information, or is it still going to be missing reactivity?
It will miss reactivity because it is static. It's not simulating in time and with all of the behavior of every semiconductor. So you can create a worst case load, and it will determine the resistance between the two, and then that's how it's figuring out voltage drop and current. So it is that basic. So you're not going to get dynamic spikes or anything like that. But if you anticipate what could be the highest corner case, can my design handle that, then that's very easily to describe. And then you save that as a configuration. So that's the idea of being able to save multiple configurations. And then you have all of these corner cases that you can run at any time by simply loading and then running. So it's not dynamic simulation like SPICE. But it is helpful. It's a quick utility to get a high level of confidence of your trace routing and power planes. Yep. Anyone else? I scared everyone with the microphone. There. Here we go. Here we go.
Hi. So it looks like this does a good job of establishing where your higher current density locations are.
Yep.
Another way that we like to view things is by the maximum rise in temperature, maximum allowable, because we do a lot of very high current designs. Are there any plans going forward to create some kind of a view like that, where we would simulate, say, at 70, allow maximum temp rise and current of maybe 10 degrees C, and then see some kind of a visual map where we'd have issues?
The best way to do that now is just through multiple configurations, so snapshots in time, because there is no simulation relative to time.
No, I'm sorry, for temperature.
Well,
not over time, just where we would do a maximum current, and it would say, hey, you said this is going to rise maximum of 10 degrees, but you're actually going to hit 15 degrees above where you want to. We'd see more of a temperature map. It's very similar to the current density one, right? It's just a different way of viewing it.
You can vary the temperature value, so you can test it under different conditions. So if you wanted to run a second condition with the higher temperature value, you can do that. So 25 degrees C is the reference, let's say, for default. And then if you wanted to do another run where that is a higher value, and then you get that snapshot of that. That's about the full range of what you can do now.
Okay.
So it's not, again, it's not going to do any dynamic analysis. So.
Yeah, I think, were you going to add, did I not clarify that? Okay.
I mean, yeah.
Yeah, I'm just, so it's just a different view, right? So we were just wondering if there was any, and you're talking about adding points maybe in the schematic to create the net list dynamically in the future. So in the future, will there be sort of a temperature map instead? I don't think that has to be a dynamic, it's still a static calculation.
Okay.
But it's based on the current densities, right? So if I have a location that's really high current density, if I put a maximum, hey, this needs to be a 10 degrees C above my simulation temperature, which say is, I don't know, say it's 100.
Right.
So say I can only get to 110. And I want to say, hey, this spot's going to exceed that based on copper thickness and thermal properties in the materials in the stack up.
So I don't know if anything like that is
Right.
planned, but we can take that.
Because we have some serious issues with some of that sometimes based on,
Temperature
65 or 70 amps running through a circuit board, right?
Okay.
So it ends up being an issue. But the current density is very helpful to let us at least pinpoint where those are.
Where the hot spots
Yeah,
are.
yeah.
So, okay. I can capture that for an enhancement. We can take that back to R&D and see what we might be able to do in a future release. So, anyone else? Yeah. Here we go. Thank you.
Hello. Oh. So in the previous example with the via that failed, how
Yep.
are the minimum and maximum settings for the vias set up? Is that a default within Altium, or do you have to click on each via and say, I have a maximum current through this 10 mil via of 200 milliamps or something?
So that was estimated with a third-party calculator, so it's not internal to the tool. And what it allows you to do is you can choose the smallest via size and the largest, and you set your smallest constraint and then the largest constraint, and anything that falls in between that, any sizing, it'll interpolate from those extremes. So the responsibility is to calculate that yourself and then apply those constraints.
So is that in the setup for the simulation then at the beginning?
Yeah, I can show you real quick where that is. So let me go back here under Tools. Go back to Configuration, so under Settings and Limits. So here we specify the smallest via used, the largest one used here, or it's based on hole size because that has the copper part. And then we did a minimum constraint and a maximum constraint from the smallest to the largest. And no matter what other different types of hole sizes there are, it'll interpolate that from those two extremes and figure that out. So that's how you can set constraints for every via size in the design.
And so will the program automatically pull the smallest and largest via size from the design, or do we have to go back and look at?
You'd have to
the
specify
list?
that.
Okay.
And that's easy enough in one of the browsers to list order by hole size. At the PCB panel, you can select via and then have them lined up to see your max and min. So, anyone else? Over on the side. So, does it look like something that would be helpful? Again, it's an extension, very well integrated into the tool, and it's basic information, but it can be very helpful to spot things early on. So, okay. And that's all we have on PDN analysis.